In this video lesson, we're going to cover two topics. We're going to cover acceleration vectors and how those look in motion maps, and we're also going to cover instantaneous velocity. So let's go ahead and get started with acceleration vectors. What I have on the screen right now are three separate situations. I have a car speeds up from rest to 25 meters per second in 3 seconds. A car applies its brakes for 4 seconds to slow it down from 30 meters per second to rest. And then finally, I have a car is set on cruise control going 40 meters per second for 5 seconds. What I'd like to do is I'd like to just draw motion maps with velocity vectors and acceleration vectors to demonstrate what's going on in this situation. So remember, for every motion map that we want to do, we always want to start out with a reference arrow. Typically, it's standard form to make your reference arrow point to the right, although it's up to you whether you want to do that or not. Now, I'm going to do my velocity vectors in blue. So the first thing I'm going to do is do velocity. And it tells me that a car speeds up from rest to 25 meters per second in 3 seconds. Generally, we want to draw a velocity vector for every second or unit of time that we're dealing with. In this case, we're dealing with 3 seconds, so I'm going to draw 3 arrows. Since the car is speeding up, I'm going to draw a small arrow, then a longer arrow, and then an even longer arrow still. Remember, you can always draw slashes to indicate the increasing lengths. The smallest length gets 1 slash, and then you get more slashes as the arrows get longer. Now those are my velocity vectors. My acceleration vectors I'm going to do in green. Remember, acceleration in this unit is always constant, meaning the arrows for acceleration vectors will always remain the same length. The question we have to ask ourselves is, which direction do they point? Are they going to point in the same direction as velocity, or are they going to point in the opposite direction? Remember, when the object is speeding up, the acceleration vectors point in the same direction as velocity. In this case, the object is speeding up, and therefore our acceleration vectors will be the same direction as our velocity vectors. And notice the acceleration lengths are the same. Now also notice that I draw the same number of acceleration vectors as I have velocity vectors for the time in which it's speeding up or slowing down. Let's take a look at the second scenario. The second scenario says a car applies its brakes for 4 seconds to slow it down from 30 meters per second to rest. So I'm going to start off with my reference arrow, and I'm going to do velocity first. It's slowing down and it's 4 seconds, so I'm going to want to have 4 velocity vectors. There's 1, 2, 3, and then notice for the fourth one, I'm going to put a dot because it stopped or comes to rest. Now I need to show my acceleration vectors. My acceleration vectors are in green, and since my velocity is pointing to the right and the object is slowing down, I know the acceleration needs to be pointing the opposite direction or to the left. So I'm going to draw that 1, 2, 3, and even though the last one is a dot, I'm still going to draw 4 to show that the acceleration was what brought it to a stop. Finally, let's do the last scenario. A car is set on cruise control going 40 meters per second for 5 seconds. Let's start out with my reference arrow. Let's do velocity first. Velocity is constant, so that means all my arrows are going to be the same length. There's 1, 2, 3, 4, and then 5. Those 5 arrows are the same length, and to show that, I'm going to do the same slash marks to show that they are equal length. Now, since the velocity is constant, my acceleration vectors are just going to look like dots since there is no acceleration. So I would draw a dot for every single velocity vector, indicating that there's no change in velocity, no speeding up or slowing down. Now, just a quick show of what's going on here. Remember, the reference arrow not only tells us where our origin is, but it also tells us which direction is positive. So in all these examples, my positive direction, it looks like, is facing to the right. Now notice how we can figure out what the sign of velocity and acceleration is. Since velocity is facing the same direction as positive, my velocity is positive, or going away from the origin. Notice since the acceleration is pointing the same direction, it also is positive. And notice when both signs of acceleration and velocity are the same, the object is speeding up. And that's actually what was happening in the first scenario. In the second problem, the velocity was still facing the right, so velocity was positive. But notice the acceleration was going the opposite direction, and so it was negative. When their signs are opposite, that is when the object is slowing down. And then obviously, since velocity is positive in the last one, and acceleration was 0, then that just means the object still is just moving at a constant velocity. Now that we've done acceleration vectors, now let's move on to the last topic of this video, which is instantaneous velocity. I want us to look back at a graph we saw back in Unit 2. Notice this is a position versus time graph. Position's on the y, and time is on the x. Now notice what this object is doing. It has a linear line for the position versus time, indicating that this velocity is constant. But let's remember why velocity is constant. Velocity is constant because the position is changing equally within each equal unit of time. That's actually why it produces a linear line. Now, what if I wanted you to take the average velocity for this entire time interval? Remember, average velocity is defined as delta x over delta t. Or in other words, it's the entire displacement over the entire time interval. So if I was looking at this graph, I would take this whole value divided by this whole value. Now, what if I asked you not what is the entire average velocity, but what is the instantaneous velocity? Or in other words, what is the velocity at a certain instant point in time? For example, what if I wanted to know what is the velocity right at that unit of time? Well, remember, you can take the velocity by figuring out what the slope is at that point. So if I took the slope at that point, that would tell me what my instantaneous velocity was. But notice, the slope at that individual point would also be the exact same slope if I were to take the average. So when the situation is where the object is moving at a constant velocity, the average velocity is also the same thing as the instantaneous velocity. So that's really simple when we're dealing with a situation in which the object is moving at a constant rate. What becomes difficult is when now we're not dealing with an object moving at a constant velocity, but when an object is speeding up, such as the one that we're finding in this current unit. Notice in this situation, the object is moving away from the origin, but it's speeding up. How do you know it's speeding up? Well, remember, the slope of a position versus time graph tells us velocity. And so notice what's happening to the slopes, let's say at these three situations, or these three time intervals. The slope in the first one is very shallow. The slope in the second one is a little bit steeper, and the slope on the final one is very steep. So since the slope is changing, the velocity is changing. And since the slope is getting steeper, that means the velocity is getting greater. Now, what if I asked you to do the average velocity for this situation? Well, that would look like this. But notice here, the average velocity slope, which is represented in green, does not necessarily match the slopes at given points A, B, or C. So the average velocity is not a good indicator of the velocities at every single point in time along this curve. So what can we do? Well, maybe we can shorten our time. After all, do we really have to take the average velocity for that entire time interval? What if we shortened it? So let's take a look at these three scenarios. Notice in the first one, the time interval has been shortened. Does this slope match the velocity better than the first situation? Yes, it does, but it's still not very accurate. Well, what if we shorten the time even more, as in the middle situation? Now that slope is starting to match even better. If we kept doing that more and more and more, we'd notice that our slope, our resulting slope, would be closer and closer to the average, or excuse me, to the instantaneous velocity at that point. Now finally, what if we didn't do a time interval, but what if we just did 1 point of time? And so that would look like the final scenario right here. If I wanted to define what's the instantaneous velocity right at this point here, what I could do is I could say, all right, what is the slope at just that point? So I'm not doing an average anymore of a time interval, but I'm actually doing just a time point, or a velocity at 1 point in time. So here's what you would do. The first thing you would do is you would draw a line that just touches the curve at that point. In math, we call this a tangent line. A tangent line is defined as a slope that touches the curve at just 1 point. And in this case, that 1 point is that 1 point in time. Once you have that tangent line, you can now take the slope of that tangent line. And remember, the slope of a position versus time graph tells you velocity. And so, we can figure out how to take the instantaneous velocity of an object that's speeding up by taking its tangent line. So let's review. First of all, instantaneous velocity is defined as velocity at an instant in time. So we're not looking at a time interval, we're looking at one point in time. So how do you find that? The first thing you do is you draw a tangent line at the point you wish to determine the instantaneous velocity. Then you find the slope of that tangent line. So let's look at the graph that's on the screen. On the screen, I have a position versus time graph of an object that looks like it's speeding up going away from the origin. What if I wanted you to find the instantaneous velocity at 4 seconds? The first thing you'd want to do is you would want to draw a tangent line that touches the curve just at the 4 seconds, which would be right here. And so I would do that just like this. Now that's not a very straight tangent line. This is why it's a good idea when you're working on a test to do this with a ruler or some sort of straight edge. Then, once you've got that tangent line, you would want to take the slope. And the slope, remember, is just y2 minus y1 over x2 minus x1. You can do that by just taking 2 points on that tangent line that you just drew. Now there's 3 ways in order to do this tangent line. The first way is what I just showed you, and that's by hand, which is perfectly fine for this class. If you're doing a lab and using Logger Pro, there is a function or a tool in there that can do it using the computer. And finally, the third way is you can use a TI calculator if you're familiar with the stat plot and the vars button. But if you're not, I wouldn't go that route. The first method by hand is plenty fine for us. So let's do an example. All right. What I'd like you to do now is I'd like you to pause the video, and what I want you to do while the video is paused is I'd like you to take the data that you see on the left of time and position, and I would like you to sketch the graph. Pause the video and then hit play to reveal that. Alright, you should now have a curve that looks something like this. First of all, take a moment and look at how I spaced my axes. On the x-axis for time, notice that I made every square equal to 0.5 seconds. Notice on the y-axis I made every square equal to 4. So you'll notice 5 squares gets up to 20, 5 more squares gets up to 40, and so on and so forth. Then I plotted my points and saw that it was a top open parabola, so I connected my points in such a way that I would represent that. Now that I've got my data plotted, I can now figure out what is the instantaneous velocity. The question says, what's the instantaneous velocity at 3 seconds? And so 3 seconds would be right here. So what I'm going to do is using a straight edge, or to the best of my ability using a straight edge, is I'm going to draw a tangent line that would touch at just that point. Something like that. Obviously it's not going to be perfect, but we can get pretty close. Now what I want to do is I want to choose 2 points that lie perfectly on that tangent line. Maybe I'll use this point right here, and maybe I'll use this point down here. Okay. So I'm going to now set it up y2 minus y1 over x2 minus x1. All right. The y2 and x2, which are right here, correspond to this data point right here. So that y value, if I were to go across, is right here, which would be 48. That x value that it corresponds to is right here, which would be 5.5. Now, let's do the y1 and the x1, which would correspond to this data point down here. Well, the y is easy. It's at 0. The x, it looks like it's about maybe 1.4. Doesn't quite get to 1.5. Now what I'm going to do is I'm going to use my calculator, and I'm going to figure out what the slope is. The top would just be 48 still, and the bottom, if I do 5.5 minus 1.4, gives me 4.1. Divide those two numbers, and I end up getting that my slope is approximately 11.7. And remember, slope tells you velocity. So my instantaneous velocity is about 11.7 meters per second. Now, I know from using my calculator that the actual value is 12 meters per second. So the closer to 12 meters per second, the better your tangent line was drawn. But remember, since you're doing it by hand, it's okay to be off a little bit. As long as you show your work that you drew a tangent line and that you took the slope of it, you'll be fine. This now concludes the video on instantaneous velocity.